Water's turning on. I think it's waking up. Get this out of the way.
I don't skip that's all that matters.
All right, everybody, let's get started. This is not a typo. This is the truth. No homework assigned today.
What? Class dismissed.
I didn't say that.
I mean, I'll take the picture.
So what made you not want to give us some homework?
That's a good question. The reason is actually the topic today. We're going to be doing a review of a lot of equations, a lot of process, and I kind of think that you need some time for that to sink in. And I want for you all to absorb what we're talking about today, and then Monday I'll give you a related assignment. So today's a little heavy on the tech side, is what I would say. Okay. Now, a couple housekeeping items. Homework 6.2 to 6.3 still being graded, but up to 6.1 is graded. 6.4 is due today. In general, I think we were talking a little bit about that before class. I think for the most part, everybody was all right with that. I want to go ahead and tell you that I'm going to have no in-class lecture next Friday. I'm going to pre-record that. I'm going to post that to YouTube. For obvious reasons, we're hosting our Virginia's conference that day. And I think it's going to kind of be an all-hands-on-deck kind of day. So I think most of your faculty will probably be civil engineering faculty, I would say, will be doing something similar. I can't speak to everybody. But if you're available, I'm sure the ASCE student chapter would greatly appreciate your help that week. Another thing I'll mention is the course eval assignments open, where if you upload proof that you've done the eval, I will give you 10 bonus homework points on top of your average. I'll say, I don't know about y'all, but this semester seems like they opened that really early. Really early. Like, I honestly think they opened it up too early, because I think that the evaluation should be done nearer to the end of the semester, because it should be an assessment of my performance throughout the semester as a whole, not half the semester, you know. But since the survey's open, I said, let's go ahead and open up the course eval assignment. It was supposed to open up on Monday, but I just went ahead and opened it now. I also went ahead and uploaded the remaining set of lecture notes for the rest of the semester. I was tweaking some things related to the coverage of shear near the end of the semester, so I tweaked some stuff coming into that. Okay. All right, any questions on housekeeping? All right. So today what we're going to do is talk about lateral torsional buckling again, but really what we're going to do is go through the establishment of the specifications in Chapter F, okay? So I want everybody to open their manual up to Chapter F. We're going to be going to 16.1. I believe it's like 30 something. Let me check and see. I think I was a little off there. Sorry, 16.1-44 is where Chapter F starts. But we're going to be reviewing some things in Chapter F. And if all I told you to do was just open up Chapter F and read it, you'd go, woo, that's a lot. So, if you like my sound effects. So what I'm going to do today is sort of break down what's going on in this chapter, but more specifically related to what we've been talking about with beams. Now, just so you are aware, if you open up to Chapter F on 16.1-44, the first thing that you see is a really big user note on the right. What that user's note is telling you is, dependent upon the type of beam that you're looking at, whether or not it's an I-shaped cross-section, a channel, an angle, it tells you which section of Chapter F you should be looking at, and then everything there on the right talks about the different limit states that you need to assess. And there's some things in there that I will tell you don't really make a lot of sense right now about flange slenderness and web slenderness. That will make sense later, but suffice it to say we're going to spend a lot of our time in section F2. So if you turn the page on 16.1-47, that'll be kind of what we're talking about today. But I kind of want to set the stage a little bit about lateral torsional buckling. So I want everybody to watch up here. So this is going to discuss what we know so far about lateral torsional buckling. So this is the buckling phenomenon that happens when beams are discretely braced. You remember I showed you that bridge in Canada where the beams kind of buckled over to the right. So let's talk about what we know so far. Okay. So the first thing that we know is that a beam's maximum flexural capacity is MP. Okay. And we also know that MP is what the capacity is if the unbraced length is 0. Remember, if you have a beam that is continuously braced, we consider its LB to be 0, and so its unbraced, or its capacity there would be MP. So what I have here on this whiteboard is sort of a generic plot that I've drawn. And on the x-axis, I've got the unbraced length. On the y-axis, I've got the nominal moment. So I propose that at LB is 0 right here, that this needs to be MP, okay? So whatever the capacity is, or whatever the plot looks like, at LB equals 0, the capacity needs to be MP. Now, we do have an elastic solution for lateral torsional buckling. And the elastic solution is what I derived last time in the previous lecture, and we ended up getting a solution that looks like this. And to be clear, we are actually going to use this solution. It's going to look a little different. It's going to be like algebraically, it's going to look different, but it's the same equation. Now, that is an elastic solution, and you're going to see what I mean there here in a bit. And by the looks of it, if you look at this solution, what's happening is that as LB gets bigger and bigger, what happens to the moment? Well, LB is in the denominator of these terms. So as LB gets bigger and bigger and bigger, the capacity goes down. So generally, if I'm looking at this plot, as we start going this way, as LB gets bigger, the capacity should start to go down. And I think that also makes sense from a physical perspective, right? If you take a beam and you start making the braces further and further apart, that beam gets flimsier and flimsier and is able to hold up less bending moment, okay? Now, remember that our solution, when we did this, it assumes that the moment is constant. And we know, and we did that because it made the solution of the differential equation easier to do. But we know that bending moments are not constant. You all had a homework problem where they weren't. We had a moment diagram where the moments were variable. And we do have a way of correcting that solution with this term CB. Now, one of the things about CB is that CB is greater than or equal to 1, right? Every CB value that you computed on the last homework assignment should have been bigger than 1, okay? And so what CB tends to do is increase the capacity, okay? But I don't care what you do to increase the capacity is limited to the plastic moment. So if I'm looking at my plot, one of the things that maybe I should recognize is that whatever the plot looks like, I can't have a capacity above that line. It can't go over MP, right? That's the limit, okay? Now, in order to explain the flexural capacity expression for beams, I want to go back to columns for a bit, and I want to talk about how the column curve was arranged. So if you remember the column curve, we did a solution, we derived a solution, and then we said that solution's great, but it's not good enough. And there were 2 reasons why it wasn't good enough. The first was geometric imperfections, the idea that columns are not perfectly straight or perfectly plumb, right? Just like I believe that golf game right there. And then busted. But then the other aspect was residual stresses. The idea that there are stresses locked into the member that propagate yielding throughout the member faster than if we assume they don't exist. Okay, and so what we ended up doing is we had 2 zones of flexural capacity as it relates to column buckling. We had an inelastic column buckling range and then an elastic column buckling range. And so what we did is basically what we would do is we would compute our slenderness and compare it to this value, and we would say, well, if we're over here, if our slenderness is less than or equal to this, then we're in zone 1, And this is our critical buckling stress. Otherwise, if we're bigger than that, we're greater than that. So we're in our elastic buckling range. So we had these two zones to consider for column buckling. Does that make sense? Okay, so now I want to talk about buckling for beams. Okay, and so for beams, what we're going to have is we're going to have 3 zones of capacity. Okay, now the 3 zones for capacity for column buckling are essentially as follows. So we have zone 1, and in zone 1, what we assume is that the capacity is just MP. It's just the plastic moment. And what we're saying in zone 1 is that the braces are so close together that we really don't need to consider the effect of buckling, and we can just assume that the capacity is MP. Then we have zone 2 and zone 3. Zone 2 and zone 3 are where we have to consider buckling, but just like columns, we have an inelastic capacity, and then we have an inelastic buckling range, and we have an elastic buckling range. Now the way that we do that is we have our curve, right? So I'm going to erase this for right now. We have our curve. What we do is we have 2 anchor points, and you're going to see these here in a bit. But we have an anchor point right here, which we call LP. We have an anchor point right here, which we call LR, okay? Now the way the curve looks is, so zone 1, in zone 1, zone 1 is going to be over here, we say the capacity is just MP. So anytime that the unbraced length is between 0 and LP, we just say our capacity is a constant MP, right? So that's our capacity. Now, between zone 2 and zone 3, or between zone 1 and zone 2, if our LB is in this range, we have sort of a straight line fit. Okay, this is what it looks like. And then anything in zone 3, we have an elastic solution, and our capacity looks like this. And so what we do is we basically call these zone 1, zone 2, zone 3. And so this would be plastic moment. An elastic LTB and elastic LTB. Okay? And so what we can do is we can compute these curves for every different W section that we deal with. So I want to show you something real quick. I have here, and I'm going to pull this up. So I have here a Desmos plot that I created. I think you all use Desmos in some of your math classes here at Marshall. Or you might some of you are shaking your head yes, some of you not. I think it depends on the instructor. But Desmos is an interactive sort of graphing calculator, but you can do some really cool stuff with it. You can do like interactive animations and things like that. So what I have here is I actually computed the lateral torsional buckling curve for a specific shape. This is for a W24 by 76. Now, just so you're aware, the units are a little different. I put the x-axis in inches and the y-axis in inch kips. By the way, if you go to Blackboard, you have the link for this this curve that you all can mess with on your own. So you all can do this to your heart's content here in a bit. But what I have here is the LTB curve actually computed for a W24 by 76. So the plastic moment in this case is 10,000 inch kips, or if you take 10,000 divided by 12, you can get that in foot kips. You can actually look that up in table 3.2 and see if that is the plastic moment for a W24 by 76. Now, the one thing that I am not talking about is the presence of CB, okay? This curve assumes that CB is 1, okay? You can see that I've got right here, this is CB equals 1, okay? So what does CB do? Well, essentially what I'm doing with CB is I am multiplying the capacity by CB, so I'm increasing the capacity, right? If CB is greater than or equal to 1, if I multiply this curve by 1.2, it's going to increase the capacity by 1.2. But what's the problem? The problem is no matter what, I don't care what CB does, you are cut off. You cannot increase your capacity past MP. Does that make sense? So watch this. So what happens is if you take CB and you start increasing it past 1, what happens is, yeah, you can start increasing capacity, but I don't care what you're increasing the capacity to, it is always going to be cut off at the plastic moment, no matter what. And that's going to create some very interesting design challenges for us later on. There are different ways to handle design of problems with quote-unquote low CB values and quote-unquote high CB values, and you'll see what I mean. But you can see how the capacity is increased as a function of CB. Does that kind of make sense? Okay, so if you understand that, then I'm going to pause that. I'm going to go back to PowerPoint here. So this, here we go. This is our lateral torsional buckling curve. And so I didn't want to just show you this. I kind of wanted to take some time and actually construct it with you so that when you see it, you're sort of like, okay, now I kind of digest it. Because I remember when I first started teaching steel design, I just said, here's the curve. It's like, whoa, what the heck's going on? There's kind of a lot going on here. And so I kind of wanted to take some time and digest it, okay? So a couple things, a couple terms. So again, the way that you determine what zone you're in is you take your unbraced length and you evaluate it against what's your LP and your LR. We're going to look at LP and LR here in a second. But basically, if your LB is less than LP, you're in zone 1, and that's your capacity. If you're between LP and LR, then you're in zone 2, and this is your capacity. If you're greater than LR, you're in zone 3, and this is your capacity. A couple of terms that are a little bit new. So first off, let me kind of lower this a little bit. We'll call this zone 1 here. I'll just call it MP, right? So a couple terms. This is a straight line fit. So this straight line fit right here is between LP and LR on the x-axis and between MP and this term here, which I'm going to call MR. And all MR is the yield moment, but the reason we call it MR is because it's the yield moment that has been reduced a little bit. It's been reduced by 30%. So it's 0.7 times the yield moment. Why have we reduced it? To account for those residual stresses that I talked about earlier. So we reduced the yield moment a little bit, and we have this reduced yield moment that defines that. This is a line, and like all lines, they have a slope. We have a name for this slope. We call this slope BF. BF for beam factor, because we engineers are very creative in our terms. We are very inventive. That was a joke, not a very funny one. All right. And that's basically it in terms of the curve, and we're going to get to the computation of all these here in a bit. Yes, sir?
Does zone 2 shrink for the CB greater than 1.0, or is the zone based on a CB of 1?
So that's a good question. In the end, you determine what zone you're in solely based on LP and LR. You do not consider CB. But the way that you compute the capacity considers zone CB. You'll see that here in a second. When you see the math, you'll see what I mean. But go ahead.
So for like the dotted lines, like those, the zone would actually, that's zone 2 for that.
No. So give me 1 sec. When you see the capacity, you'll go, okay, it doesn't really matter. All right. So just bear with me. All right. Okay. So let's look at the capacity. Let's look at the terms a little bit. So first off, the first thing I think you need to do is you need to figure out what zone you're in, and that means you need to determine LP and LR. And here are the equations, and I think that's the longest equation I have in any of my slides. But look, I have a smiley face, and I say relax. We'll see in a minute or two that we are not going to have to calculate this, but this is probably a very, very nuts equation. Another thing that might be a little counterintuitive is if I were to ask which equation is harder to derive, which equation takes more effort to derive. It may be counterintuitive, but that one's a lot harder, okay? This one is actually just algebra, because all you do is you take that critical buckling solution, set it equal to 0.7 my, and solve for the length. yeah, it's a nasty equation and there's a lot of algebra, but when it's all said and done, you give it about half an hour and you could actually come up with this. This is actually pretty easy to derive. This one takes a lot of experimental testing, a lot of numerical modeling, a lot of judgment calls. It's not very easy to arrive at what the cutoff should be for what you should, or when you should consider buckling and when you shouldn't. This one takes a lot of work. But again, LP and LR, you are not going to have to compute, and I'm going to show you that here in a second. Now, to answer Mr. Odell's question, so Mr. Odell was saying, wait a minute, what about that zone, right? That cutoff zone. If you are in zone 2, what you do, here's how zone 2 works. What you do is you basically compute the capacity assuming CB is 1, and then the answer is to take the minimum of the capacity times CB or phi and P. You just take the minimum. So you don't really have to like find a new LP or LR, because in the end, the capacity is either going to be lower than MP or it's just going to be MP. So it's actually pretty easy, okay? Now, if you open up chapter F and look at the expression for zone 2, this is what it looks like. It's kind of long, okay? But what I propose we can do is rewrite it in this fashion. And what I'm basically doing is I'm taking this term here and I'm rearranging it a little bit, and I'm basically taking this constant fraction and calling it BF because it's just the slope of the line. All this is just y equals mx plus b. That's really all this is. And this BF is the slope of the line. Now, if you notice in this zone 2 expression, if you open up the spec, none of the phi values are in the spec. None of the phi values are in chapter F if you turn to 16.1-47. This is directly from chapter F. None of the phi values are in the equation, but the one I'm telling you to use has all the phi values. Why? Well, you'll see that here in a second. Because it's a lot easier than you would think. Zone 3. Zone 3 is the only one that takes a little bit of effort. What we do in zone 3 is we compute this. This is the elastic critical buckling stress. And I'll tell you, this is actually the same solution that we derive. It looks different. I'll tell you, it looks different. First off, it is numerically equivalent. It's just been rewritten a bit. We take the solution that we derive from the differential equation and just throw some algebra at it, so this is the same answer. But the reason why we wrote it this way is because this is the solution for compact W shapes. If you're looking at plate girders or you're looking at other types of elements in bridges or what have you, the equations are somewhat different. But if you formulate it in this pattern, you find that the equations for W shapes and the equations for plate girders are very, very similar. So it makes it a lot easier for you as a structural engineer to handle routine elements and very non-routine elements with very similar math. So it's really meant to help you all out when you're doing more complicated or more advanced steel design. Now, when you're using this expression, you do need a lot more section properties. You need RTS, which is sort of like a radius of gyration for torsion, for LTB. You need a J, a torsional constant. You need a section modulus. You also need this term H naught. H naught is the distance from the center of the flange to the center of the flange, but you don't need to compute all that. If you go to table 1.1, you can look all that up. The only thing that you need that you probably can't discern right from the equation is this term C, and C is 1. C is 1 for I shapes. It only changes if you're looking at I think C shapes. There's a slight formula for that. One thing I will say with zone 3, be very careful with your LB term, because LB needs to be in inches, okay? Because if you notice, you're taking LB over RTS. LB over RTS, and RTS is in inches. And don't worry, for each of these zones, we're going to have examples. We're going to go through it. So it's not going to be as scary as it looks. And I got a nice little flow chart that'll make life a little easier for you. Okay? Everybody with me so far? So what you do is you compute a buckling stress, and then again what you do is you take the minimum of whatever you're computing from zone 3 or the plastic moment. And that's how we handle that cutoff from MP. So it's actually a lot easier than you would think. We just sort of compute the capacity and say it's either what we compute or MP, whichever one's smaller. So, everybody with me so far? So, why did I say that you don't need to worry about computing all this stuff? Remember table 3.2? Let's open up table 3.2. Go to table 3.2. I told you by the end of this table 3.2, you were going to know everything about what was going on in table 3.2. I mean, look at all the data that is packed into this table. This is an incredibly useful guide. I think this table takes the cake for probably the most useful table in the whole manual. Because, look, we have our FEMP, but now we have FEMR. Remember, we weren't looking at that before. Now we have it. Now we know what FEMR is. What about this FEBF? What is FEBF? FEBF is the slope of that line, right? Done. What about LP and LR? LP and LR help us figure out what zone that we're in. We also have the moment of inertia, and we have the shear capacity. And we will discuss the shear capacity during Monday of Dead Week. We'll talk about how to compute shear capacity. So, again, as we've seen so far, shear capacity doesn't really matter all that much, but we are going to cover it. So again, remember I told you there's this really nasty equation. You're never going to have to compute it because just look it up. Sound good? Now, what I have done here is I've taken all those equations and all that math and I've put it in this. This is one of those like greatest hit slides. This is definitely one that you can put on a formula sheet. But basically what it does is it in this slide, this is everything that you need to know for flexural capacity of beams. This is probably one of the most useful slides I have in all of my lectures. So if you're in zone 1, there's the capacity. If you're in zone 2, there's the capacity. If you're in zone 3, there's the capacity. Every term that you need, I even went ahead and threw the CB formula up there as well. So everything all packed in one single cohesive place. Very useful flow chart for you all going through some of these problems. All right. All right, let me stop for a sec. I want to see if anybody has any questions. Okay. All right. So I want to go into an example, okay? But we're going to do this example, but I'm not going to give you a homework assignment today. I'm going to give you a homework assignment on Monday because we're going to do another example and make sure that we're comfortable with this, okay? So I have a beam, and it has been subjected to some dead loads and some live loads, and we've got a bracing configuration shown, and I want to know whether or not this beam is sufficient in resisting the load that we're looking at here, okay? And the cool thing is this is a W24 by 76, so it actually mimics what I have here on my Desmos chart. So we might actually use this and see if we're kind of getting the same answer. So, because we can actually visually see how CB affects everything. We'll have some fun with it. So I'll give everybody a sec to jot all this down, and then we'll get into it. Now, while you're writing this down, this little box here in gray, I'm going to say a few words about this, but we'll get into a little bit more detail about this in some later lectures. But I say here that there are two, basically what I'm saying in this box is that there are two unbraced segments. The segment from the left support to the middle and from the middle to the right support. And for each of those segments, I could theoretically do an evaluation, compute the moment demand, compute the moment capacity, see how it performs. But I propose to you that for this problem, I only need to look at one of them because the beam is symmetric with respect to loading, geometry, and bracing. So I really only need to look at one of them. And a good way of assessing that is to look at the CB terms, okay? So if you remember in the homework assignment, you can go to table 3.1 and actually just look up the CB terms, right? And so for a lot of very simple loading conditions, we can look up CB. What is the CB value going to be for each of these segments? You should know because we just did this one. 1.3. 1.3, right? So CB for this segment, put this over here. So CB is 1.3 for each of these segments, and so really all we need to do is consider one of them. We don't need to worry about the MA, MB, MC, and max, any of that, because we can just look it up, okay? And so I found that in table 3.1 on 3-18, so. Okay, all right. So what I'm going to do is, so let me scroll down a little bit. So first thing I'm going to do, let me take this and move it down a little bit. So the first thing I'm going to do is I think I need to determine what zone I'm in, okay? So let me do this, okay? So the first thing I need to do is determine the zone. Now, what is LB for this problem? Say it again? 15 feet, exactly. This is because that's the distance between the braces, okay? Okay, and what's really important to recognize is that LB is not 30 feet, it is 15 feet. 15 is from brace to brace, brace to brace. LB is 15 feet. Now, the section that we are looking at is a W24 by 76. Now, if we're looking at a W24 by 76, what is LP? And what is LR? So somebody help me out. For a W24 by 76, what is LP and LR? Has everybody brought their AISC 15 edition truck in?
6.78, 19.5.
6.78 and 19.5. Always have to do that. Okay? So 6.78 and 19.5. So what zone are we in on this problem? Zone 2, right? Because LP, so if we go over here, LP is like 6.78 feet. LR is 19.5 feet, and we're 15 feet, so we're about right there, right? So that's right in zone 2. So what I'll do is I'll say LP is greater than LB. Sorry. Whoop. Wait, I'm sorry. My coffee hasn't kicked in. That's what I want. I need coffee. So, zone 2. We're in zone 2. Okay? Now, okay. Everybody with me so far? Now, this is where this flow chart, I think, will really make your life a lot easier. So let me bring this back up here. So I copy and pasted this flow chart from the slides right into the calculations. So if we're in, so I think we're all in agreement that we're in zone 2. So if we're in zone 2, this is our capacity, okay? So we're going to need some quantities in order to be able to compute the capacity. Okay, so what are we going to need? All right, so let's see. We're going to need CB, but we've got that. That's 1.3. All right. What about phi b mpx. What is that for a W24 by 76? Do we need to compute it? No, we just look it up. What is phi b mpx for a W24 by 76?
750.
750 foot kips. What about our beam factor? What's the beam factor? That's the slope of this line right here.
22.6.
22.6 what?
Kips.
Kips. And if you think about it, that makes sense that the units are in kips because we're talking about change in Y, which is in moment, that's foot kips. So change in foot kips over change in feet. So foot kips divided by feet, that's kips. Okay? We're going to need LB, but we already determined that's 15 feet. And we're going to need LP, but we already determined that LP is 6.78. So the way I'm going to handle this is I'm first going to compute this upper row inside right here. So therefore, CB times B MPX minus B BF LB minus LP. See, the equation looks really intimidating. It's really not, because it's just 1.3 times 750 foot kips minus 22.6 kips times 15 feet minus 6.78 feet. And so when we chug that out, what do we get? All this is, by the way, this is just linear interpolation. This is just interpolation on that line and then upping it by 1.3. That's all it is.
$733.
733, I think like 0.5. And I think I got a second on that.
Yeah.
So, if I want to compute the capacity, how do I compute the capacity? I take the minimum of all that hullabaloo and phi and p. So, therefore, BMN is the minimum. And I'll tell you how I kind of write it. I say CB times all that, or BMPX, because I'm lazy and I don't want to write all that all over again. So that's the minimum of 733.5 foot kips, or 750, and BMN is 733.5 foot kips. That's it. That's really the only thing that's different from a continuously braced beam is that. And I'll show you what happens after that here in a second. So remind me, hold on, what was LP and LR? LP was 6.78. And LR was 19.5, was that right? Okay, all right. So I just want to take a look at something. So if we go back to the Desmos plot that I showed you earlier, so here's the Desmos plot where we can change the CB value. What was CB, 1.3? So that's CB, okay. Ooh, don't need the weather. All right, so let's see. LP is 6.78, 19.5, 15. What's 15 times 12, by the way? 180? So 180, we're about right there. And if I go up, that's my capacity. My capacity is just shy. Think I did something right there? So There we go. Everything's kind of lining up. Sound good? So, if I wanted to evaluate whether or not this section is valid, I need to do some structural analysis. So the structural analysis, what I need to do is I need to compute MU and VU and all that. Okay, can I go ahead and scroll away? All right. So remind me, the beam was this, and then we have a distributed load. We have a W dead of 1.25 kips per foot, a live load of 3 kips per foot, right? So what I can do, and by the way, I'll say, I think we were told in the problem that the self-weight of the beam was included in this dead load, so we don't have to consider that 76 pounds per foot for the W24 by 76. It's already been included. So what we'll do is we'll say, okay, make sure I'm not running over on time here. So what we'll do is we'll say that our dead load moment is WL squared over 8. Okay. And I can go ahead and do that for you. I think it's 140.6, although you might want to check and make sure I didn't make any mistakes. Did I get that right? How'd I do? Did good? Okay, by the way, let me just go ahead and write this here. So, phi mn is 733.5 foot kips. So M dead is 140.6, ML is 337.5. I do good? And so therefore, MU (1.2 dead plus 1.6 live), and I think I'm getting 708.8. So MU is that. So is the beam safe? Yeah, it is, right? So what we'll say is phi mn greater than mu. Now, if we want, while we're at it, what we can do is a shear analysis. We can do a deflection analysis, but none of that is going to be any different than what we did before. So, like for example, if we're looking at, let's say, shear, okay. So shear, let's do this. So shear is WL over 2, which is, well here, let me just do this. Let's just make this easy. So shear is 1.2 times the dead load shear plus 1.6 times the live load shear. And when you chug that out, like you get out, I'll go ahead and tell you, you get 94.5 kips. But somebody help me out. What is phi VBN for a W24 by 76? 315. So 315 kips, right? So again, we've got a VBN of 315 kips and a VU of 94.5 kips. Are we good? Yeah, we're good. Like, again, shear is not a big deal, right? It's just not a problem. So, all right. And finally, if we want to do the deflection check, again, deflection, no different than before. We have a W of 3 kips per foot, an L of 30 feet, an E of, what's the E for steel again?
20,000.
There we go. Want that number burned into the back of your head by the time you graduate from Marshall University. And then I, what is the moment of inertia for a W24/76? Again, it's all in table 3.2. Man, table 3.2 is just great, man. Everything you need is packed in that one guide.
So, is the VBN value in that table too?
Yes. Yes, it is. When it's all said and done, we're going to learn how to compute VBN, but I'm putting that off to the end because as we're seeing, shear's not really mattering all that much. We're going to cover it, but I'm not worried about covering it now. All right, what do we got for a moment of inertia?
2850.
2850?
2100.
Did I get the right one? 2100?
Oh, yes, sir. 2100. So
So what we'll do is, to clarify our notation, what we'll say is we'll say that delta L maximum, so this is the actual deflection, is 5 WL to the 4th over 384 EI, which is 1.20, sorry, 3 kips per foot, 30 feet to the 4th, and then times 1728. Okay, and since we're running out of time, I'll go ahead and tell you that when you chug this out, you should get 0.898 inches, and then we can compare that against our limit, which I believe on this problem was L over 360. Is that what we were told? So L over 360, again, deflection limits in steel design are very client driven, or there's some industry standards like L over 360. So 30 feet over 360, and again, multiply that by 12 inches per foot so that it all comes out in inches. And 30 times 12 is 360, so 360 over 360 is 1 inch. So our max is less than our limit. So is the W24/76 adequate for this problem? Yes. So what we're going to do today is not assign homework, because I want what we did today to sink in. On Monday, we're going to do another one. And the other one is going to be a different zone. Because I think you should have some experience with zone 3, then we'll do an assignment. Once we're good with that, we'll talk about design. And designing for LTV, I'll level with you, it uses one of the craziest looking design guides ever. But it's actually pretty easy to use. And with that, that's all I got. I'll pull up the QR code again for anybody who missed it, but you all have a great weekend, and let me know how the golf game goes. I will see you then.